We can think of symmetric key systems as sharing a single secret key between the two communicating entities. This key is used for both encryption and decryption. Symmetric key systems relies on the sender and the receiver sharing a secret key by using some secure method whereby the entities can first agree on a secret key that is known only to them. The components of a symmetric key system are detailed as follows. A block cipher operates on groups of bits, typically groups of 64. If the final block of the plaintext message is shorter than 64 bits, it is padded with some regular pattern of ones and zeros to make a complete block. Block ciphers encrypt each block independently, so the plaintext does not have to be processed in a sequential manner. This means that, as well as allowing parallel processing, for faster throughput, a block cipher also enables specific portions of the message to be extracted and manipulated. A stream cipher generally operates on one bit of plaintext at a time, although some stream ciphers operate on bytes. Stream ciphers can be classified as either synchronous or self-synchronizing. In a synchronous stream cipher, the key stream output is a function of a key and is generated independently of the plaintext and the ciphertext. In a self-synchronizing cipher, the key stream is a function of the key and several bits of the cipher output. Because the key stream outputs depend on the previous n bits of the plaintext or the ciphertext, the encryption and decryption key stream generators are automatically synchronized after n bits. Asymmetric or public key systems are based on encryption techniques, whereby data that has been encrypted by one key can be decrypted by a different, seemingly unrelated, key. One of the keys is known as the public key, and the other is known as the private key. The keys are, in fact, related to each other mathematically, but this relationship is complex, so that it is computationally infeasible to calculate one key from the other. Thus, anyone possessing only the public key is unable to derive the private key. They are able to encrypt messages that can be decrypted with the private key, but are unable to decrypt any messages already encrypted with the public key. Public key algorithms can allow either the public key or the private key to be used for encryption, with the remaining key used for decryption. This allows these particular public key algorithms to be used for authentication. Public key algorithms place higher demands on processing resources than symmetric key algorithms, and so tend to be slower. Public key encryption is therefore often used just to exchange a temporary key for a symmetric encryption algorithm. The security of any system using encryption should not be compromised by knowledge of the algorithm used. The strength of a cryptographic algorithm is difficult, if not impossible, to prove, as it can only be shown that the algorithm has resisted specific known attacks. An attack in this context is an attempt to discover the plaintext of an encrypted message without knowledge of the decryption key. Cryptanalysis is the science of breaking a cipher without knowledge of the key and often the algorithm used. Its goal is either to recover the plaintext of the message or to deduce the decryption key so that other messages encrypted with the same key can be decrypted. It is the study of methods for obtaining the meaning of encrypted information without access to the secret information, which is normally required to do so. An example of cryptology is as shown in the figure, where new and more sophisticated mathematical tools may emerge that substantially weaken algorithms previously considered to be immune from attack. Confidentiality between two communicating nodes is achieved by using an appropriate encryption scheme. Data is encrypted at the sending node and decrypted at the receiving node. Encryption will also protect the traffic between the two nodes from eavesdropping to some extent. However, for encryption to be used effectively in networks, it is necessary to define what will be encrypted, where this takes place in the network, and the layers that are involved in a reference model. The implementation of encryption in packet-switched networks must ensure that essential addressing information can be accessed by the relevant network devices, such as switches, bridges, and routers. Encryption is broadly termed link layer encryption or end-to-end encryption, depending on whether it is applied and reapplied at each end of each link in a communication path, or whether it is applied over the whole path between end systems. Link encryption, sometimes called link level or link layer encryption, is the data security process of encrypting information at the data link level as it is transmitted between 2 points within a network. Link layer encryption is independent of network protocols. However, each link will typically use a separate key to encrypt all traffic. This makes the encryption devices specific to a given medium or interface type. In a large network where many individual links may be used in a connection, traffic will need to be repeatedly encrypted and decrypted. Because the process protects the message in transit, link encryption is very useful in situations where the security of the transmission line is not assured. However, because the message is decrypted at each host in the transmission path, vulnerability can arise at a link when the message must be transmitted between hosts that are not known to be secure. While data is held at a node, it will be in the clear and unencrypted and vulnerable. Another disadvantage is the need for a large number of keys along any path comprising many links. Hardware-based encryption devices are required to give high-speed performance and to ensure acceptable delays at data link layer interfaces. The effectiveness of link layer encryption depends on the relative security of nodes in the path, some of which may be within the Internet. The question of who can access nodes in the Internet then becomes a significant concern. When applied to terrestrial networks, link layer encryption creates problems of delay and expense, but it is particularly useful in satellite links because of their vulnerability to eavesdropping. In this case, the satellite service provider takes responsibility for providing encryption between any two earth stations. End-to-end encryption encrypts clear data at source with knowledge of the intended recipient, allowing the encrypted data to travel safely through vulnerable channels to its recipient, where it can be decrypted. End-to-end encryption at network layer is normally implemented between specific source and destination nodes, for example, by IP addresses. As information contained in IP packet headers is not concealed, eavesdroppers could perform traffic analysis based on IP addresses, and information in the headers could also be modified for malicious purposes. In application layer encryption, end-to-end security is provided at a user level by encryption applications at client workstations and server hosts. Of necessity, encryption will be as close to the source and decryption as close to the destination as is possible. In end-to-end encryption, at application layer, only the data is encrypted. Some other method of providing assurance of the integrity of a message is therefore needed, some kind of concise identity of the original message that can be checked against the received message to reveal any possible discrepancies between the two. This is the purpose of a message digest. It consists of a small, fixed-length block of data, also known as a hash value, which is a function of the original message. A common use of a hash value is the storage of passwords on a computer system. If the passwords are stored in the clear, anyone gaining unlawful access to the computer files could discover and use them. This can be avoided if a hash of the password is stored instead. The security of this method relies on the hash function being computationally irreversible. In other words, it is easy to compute a hash value for a given input string, but extremely difficult to deduce the input string from the hash value. Hash functions with this characteristic are known as one-way hash functions. For a hash value to give an effective assurance about the integrity of data, it should also be computationally infeasible to generate another message that hashes to the same value. Hash functions that provide this characteristic are said to be collision-free. A brute force attack on a hash value can be either an attempt to find another message that hashes to the same value, or an attempt to find two messages that hash to the same value. A message authentication code is similar to a one-way hash function and has the same properties, but the algorithm uses the additional ingredient of a secret key, and therefore possession of the key to perform the check is necessary.